Hey gang, so I'm going to try and do this video on the introduction to integration, which is the area under the curve. Now we kind of talked about it at the very beginning of calculus. We talked about the tangent problem, and we destroyed that in calculus unit 5A, where we learned how to take a derivative and find the tangent line of a function anywhere it happened to be. And now what we're going to do is, let's say we have the same function. How do I find the area under the function? Going off what you already know about area, you know geometry. You know lots of geometry. If I were to draw like rectangles under here, like all of these, pretend like from A to B, I draw rectangles and I try to make them fit in here as best I can. And you can see where we have this little piece left off and this and this. And so we don't get an exact area, but rectangles, they do kind of work. What if I made the rectangles really, really small? Oh, you've heard that term before, really, really, really. That is when you make the rectangle so small that you couldn't even slip a piece of paper between them. They're just incredibly close together. And you line them all up, and you end up getting the area under the curve. Oh, that's a whole lot like a limit between A and B. As we get closer and closer to however many rectangles we put in there, infinitely many, what's the area under the curve? Okay, the other thought is, using geometry, what if instead of rectangles, what if I change the shape? What would this be? Long side here. These are, hopefully you're thinking, trapezoids. The trapezoid kind of fits a little better, doesn't it? You don't see near as much white space as you do on this. So we're going to look at two different methods. One's going to be a little more rectangular, one's going to be a trapezoidal, and one's going to be, well, what if we just use calculus to solve this? Because probably that's going to be the easier way. All right, so let's talk about this rectangle method. I want to put this, I was trying to think about, I'm going to put this over here. So I'm going to say the rectangle method. Let's say divide the interval into equal subsections, and then let's say divide interval, and that's kind of important. The interval here is A to B. The interval here is 0 to, it looks like 5. There's 1, 2, 3, 4, and 5. Yeah, that's from 0 to 5. Divide an interval up into, and very important, we need to say equal, meaning that the distance here is always the same. We couldn't have a big one here and a little one here and a big one here and a trapezoid, we could do that, but rectangle, you're trying to keep it all uniform. Divide the interval up into equal subsections. And then we're going to divide, and you know how to write the interval A comma B into n equal subsections. Can't say that very fast. Subsections. And we're going to create a rectangle in each one. And create a rectangle in each one. That's the rectangle method. Now, the trapezoid method, I'm going to come back later and put a more formal definition here, but think of it as the same thing. Divide it up. This time we don't necessarily have to have equal shaped trapezoid, but we're going to divide it up into the trapezoid, and then there's a whole nother rule. Let's say to be announced, and we'll come back and do that later, because it's going to be the same idea. We're going to divide it up into trapezoids from A to B, and then we're going to create subsections, and we're going to find the area of each trapezoid and add it together, right? I mean, that's really all we're going to do. But there's going to be a whole nother process with it as well. Okay, here's something to know. You know what a derivative is. Okay, if I take f of x, we know that f prime of x is the derivative. Okay, so keep all this new jargon in your brain for a second, because here it comes. We're going to call the area, we're going to say the area under the curve is capital A of x. That stands for the area. It's going to be represented kind of like a function, A of x. Okay? Now, here's what we're going to say. If A of x, it's fascinating when we do this, y'all, like so fascinating. If A of x equals the area, I guess I could have written it that way, under the curve. These are my first time to write the notes on here, so I'm not sure how they're going to fit. The area under the curve of a function we'll say for some function, oh, I wrote it like you would, for some function, f of x. And we'll have to say it's on an interval from, like, we'll call it from A to B. So in other words, A of x is the area under the curve, and it's represented by this function here, okay? If A of x equals the area under the curve of a function on a given interval, okay, we're always on a given interval, this is what's fascinating, then A prime of x. Now think about that. If this is the area, if I take the derivative of the area, guess what that equals? You won't guess it. It's amazing. It equals f of x. It equals the function. Okay, so I am going to box that in because that is super important. I didn't really leave myself enough room to box it in, but I'm going to box it in because that's the whole gist of integration. Okay, this implies that if you find the area under the curve, which is A of x, if you find that area and you undo it, you take the antiderivative of it, then you get the function. All you have to do is undo it, okay? But you're going to be working backwards. So it's kind of interesting how that works. But anyway, so let me see if I can find a different color here. Let's wonder if we could put that on her. This implies that to find the area under the curve of A of x, let's just put we must, let's say undo. Let's just call it undo. We must undo A prime of x to find, oh, I'm not going to have enough room, A of x. So if we start with A prime of x and we undo it, we get A of x, right? Okay, I'm going to highlight that. That's the whole goal. That's where we're going with this. That's the whole goal. We will use our calculator a lot on that. Our calculators will allow us to do that quite a bit. Okay, so let's just start with some simple stuff that's kind of easy. This one right here is going to kind of prove my point of the area, okay? So let's see, f of x equals x plus 1. Find the area on the interval -1 to x. Okay, so what we're going to do, we're going to do lots of drawing. I was just looking around. I don't have like a ruler. Okay, I'm just going to, yeah, okay. I'm going to graph f of x. F of x is x plus 1. So I'm going to go 1, 2, 3. 1, 2, 3. 0, 1, and then if x is 1, y will be 2. If x is negative 1, y will be 0, so that will be negative 1. Okay, so I'm going to go up. Say it looks something like that. All right, so this is f of x. Now I'm going from negative 1 all the way out. How far? I'm going out to x. Okay, I don't know where x is. I'm just gonna call it x. So this is the distance from here to here is x, and then I need to figure out how long is this. Well, it would be x, and you're not subtracting 1 because think of it like this. You're actually going a whole 1 step, so it's 1 plus x. So the distance here is x plus 1. That's how far I'm going. Okay. So I'm going to draw this up. What shape do you notice? Yeah, you notice a triangle, right? All right. So this point right here, what is that point right there? I kind of need to know the height of it. Well, we're going to get to that. I'm going to color this in. All right, so I want to know the area under the curve. And I'm like, oh, it's a triangle. Okay. I was sitting here thinking I needed to know that, but I probably don't. Okay, so the area of a triangle. I do 1/2 base times height. You may do something different, whatever you happen to do. I'm going to do it this way. So I'm going to go area equals 1/2 the base, which is x plus 1, times the height. How tall is it? It goes from 0 all the way up. How far? Well, let's think about it. If I plug x, remember you're going to be evaluating this. You go out x, where do you end up at? You end up at f of x, right? This right here would be f of x. That right there. So that ordered pair right there would be x, comma, f of x. Well, f of x is x plus 1. So the height of this is x plus 1. I'm going to say that one more time just to make sure you follow me. So you see the distance here is x plus 1. How tall is it? Well, if I said how tall is it at 1, you would say, well, let me see. Let me plug 1 into the equation. 1 plus 1 is 2. You would say it's 2. If I went to 2, you would plug 2 into the equation, and you would say 2 plus 1 is 3, and you'd say it's 3. If I go out to 4, you would plug 4 in here and say 4 plus 1 is 5. If I plug x into the equation right there where x is, x plus 1 is how tall that is. So this side over here is x plus 1. I just need to multiply this out. So here we go. So the area equals 1/2. I'm going to multiply that out in my head. X squared plus 2x plus 1. And then I'm going to go ahead and take that 1/2 across. 1/2 x squared plus x plus 1/2. Now, I know the area, so I'm going to change this and I'm going to say a of x, because that's all I did, is 1/2 x squared plus x plus 1/2. Now, what we said earlier was that if you take a prime of x, we should get f of x, right? That's a of x. Let's take the derivative of it. So I'm going to come over here and I'm going to say a of x equals 1/2 x squared plus x plus 1/2. And I'm going to say a prime of x equals 2 times 1/2 is 1. So that will be x. This is to the first power. Bring that 1 to the front. X to the 0 power is just nothing. It's just a 1, so it's just a 1 here. And when you take the derivative of a number, it goes away. Oh. Remind me again what f of x was? F of x was x plus 1. Mind blown. They're the same. A prime of x is the same as f of x. Okay, so now we kind of know that, okay, if I can find the area, if I take the derivative of it, I should get back to the function. That's actually one way you could check your work if you wanted to. Okay, so let's go on to my next one. Find the area under the curve of x squared between the interval from 0 to 1. Okay, take a second and draw that. Oh, I'll use black to draw. X squared is a parabola. That goes up. I'm going to say this is 0. I'm going to come out here to 1. I want to know the area under this curve. And we want to go from, this is 0 to 1 right there. And this is f of x. Okay. This one's not as easy, but it's not super difficult either. We're going to use some things that we know. Oops, sorry. Some things we know, there we go, to help us solve this. One thing I know is that a prime of x equals f of x. So while I don't know the area, because I can't really say it's a triangle because there's a little bit of a curve. So it's not exactly straight if I were to do a straight line. But I know that a prime of x equals f of x, and I can take the derivative, right, if I needed to. So I'm going to say that a prime of x equals x squared. So here's my question. Can you undo that and figure out what a of x might have been? And so I'm going to give you some ideas. I'm going to do this in blue. This is kind of like it's a guess and check, y'all. There's no exact answer because we really don't know. I'm going to say that a of x could have been, if it ended up as a squared, that means it had to have a 3 up there, right? It had to start with that. Because if I were to take the derivative of this, a prime of x would be 3x squared. The thing is mine didn't have a 3 in the front. And so I'd be like, okay, so I'm really close, but I can't have a 3. Well, if I wanted to get rid of the 3, if I divided by 3. So what if my a of x was like 1/3 x to the third? Then that would give me a prime of x would be 3 times 1/3 would be 1. And I would just get x squared. Yeah, that works, right? It had to be that. Okay, so I'm with you because I kind of agree on that. But let me throw a curveball at you. What if I told you that a of x was 1/3 x to the third, I'm going to say plus 7. And you're already like, no, that can't work. That won't work at all. Well, let's see. Let's take the derivative of that. A prime of x would be 3 times 1/3 would be 1. That would be x squared. But the derivative of a constant is 0. Oh, well, yeah, that does work because the 7 goes away. It's gone. Interesting. So there must be a way to figure out how to find the antiderivative, and there kind of is. Could I put 100 right there? I could. Could I put a 0.001? I could. really, I could put 1/3 x to the third power plus any constant I want to put there. I could put pi there, I could put e there. Whatever constant I want is what I'm going to put. That is a of x. And this implies that a prime of x, which is what we already know, is x squared. That works. Now in Cognity, they ask you some questions about this. They give you some really interesting scenarios on that. Okay, now we're going to use some mad algebra skills, y'all. Y'all ready for this? I'm going to actually tell you that C was actually 0. Because you're kind of thinking, well, is C the intercept? You know, what could I just say plus C and C was 0 and so it's 0? Sorta. But here's what I'm going to say. I know that a of x is 1/3 x to the third power plus c. I'm going to pick a number on f of x, okay, on f of x that I could plug in and check and figure out what c is. So on my curve, I could do 1, 1, I could do 0, 0. I can use any of these points. I'm going to use 0, 0 because 0, 0 is easy to use. So I'm going to use the point 0, 0. This is the y value. That's a of x. So that's here. So 0 equals 1/3 times, this is the x value. So I'm going to plug 0 in here, cubed, plus c. 0 equals c. What? So c is 0. So you know what that tells me? Is that a of x equals 1/3 x cubed. That was what a of x actually equals. So can you solve for it? Heck yeah. If I need to, I can. All right. I'm going to stop the video and do the next one.